Hello, Camille. Hello, Toru, Herman, and Safa. And Lauren, hello. The Thursday crew is here. Thursday, I like the Thursday crowd. Don't tell Monday and Tuesday crowd. Which, by the way, Safa, you're also part of the Tuesday crowd. So the fact that I like the Thursday crowd better than the Tuesday crowd, just saying.
Respect.
just have to look at the variables here.
Yeah.
But welcome, everybody, to my no longer so humble abode. I have decorations now. This, by the way, I just need to keep you guys informed because no one else in my life cares. But if you guys remember the first day of class, I was on the ground because my desk wasn't built yet, but I had high hopes for it. I don't know if you can. Oh crap. Okay, I can't move the webcam, but look at this bookshelf, other bookshelf, Dutch angle, full corner desk. It only took 7 weeks, but we finally have something here. How's it going with you guys?
I just made some ramen. That's it.
That sounds like you're chilling.
I am. It's spicy kimchi. The smell, it's kind of making me hungry, but it's too hot to eat right now. So I'm gonna be focused right now. Then I'm gonna tap out of the lecture later. Not like leave the lecture, but not pay attention later because I'm gonna be eating. But what's up?
So do you like ramen for ramen? Or do you like the convenience?
Convenience.
I went to I went to like a gourmet's the right word, but like a high end ramen place in Nova one time, and it confused me. Those felt like distinct concepts to me, high end and ramen, but it was delicious. I mean, I liked it a lot. The question is, would I have liked it better if it wasn't ramen? Like, I like ramen. Don't get me wrong. I don't know. I've never loved ramen. I was really hoping someone would back me up here, but I guess I'm alone. Anyway, so, but 4:03. So let's just get started. If no one has anything else to distract me. Well, I guess that just means you guys like discrete math so much. Like, no, we don't want to talk about basketball and ramen and your desk. We'd rather do discrete math. And I know all these things are interesting. Therefore, discrete math must be more interesting. So welcome, everybody, to discrete math. Let me start sharing my second camera to get our whiteboard going. And yeah, today, if we have time, I hope we will. We have a chat already. What's happening in the chat? The least painful math. That's fun. That's a great way to look at it, stuff. I mean, I think that all math isn't painful, but it is kind of the most fun math because it's like, you know, I'm not asking you to solve a derivative or do trig subs or anything like that here. I'm just asking you like about cool stuff. And today, if we get to it, we're hopefully going to get to literally what I think is the most beautiful proof in mathematics. And it's largely considered that. And someone maybe died over it. And it's part of the reason I'm a mathematician. So it's kind of nice. So 50-50, we'll get to it. But anyway, the reason it's so beautiful is because we're talking about a new thing today that we started last time, and that is direct proofs, or indirect proofs. This is chapter 4.7, and we're talking about indirect proofs. And so far, we've gone over 2 forms of indirect proofs, and those are the only 2 we're going to go over in this class. Those are actually, I don't even know anymore. Maybe the only 2. Those are contrapositives and contradiction. Contrapositive was real simple. A contrapositive proof just said instead of proving something directly, instead of proving it if then directly, prove it's contrapositive. That makes total sense. Contradiction is even cooler and a little different. That's what we're doing when time expired. So let's remember what a contradiction proof is. So last time I went through a whole wacky thing where we went over Legally Blonde, and it was awesome. But really, the bones of it is, like, stripping away all the BS there. The bones of a contradiction proof is to prove that for all x and d, p of x is true. Assume the opposite. And this is the brilliant part of it. This is like some kind of weird Avatar philosophy where you like go the reverse direction, or some like car, yeah, go left to go right, whatever they're doing in that movie. Assume the opposite. Assume that there exists an x and d such that not p of x is true, right? Because that's the opposite of this, that's the negation. Assume that. Because then, if we can show there exists an x and d such that not p of x is true, or so if we can show that this logically leads to a contradiction, then it must be false. So the idea is you assume the opposite, and if you can prove that the opposite's true, it will lead to a negation, or sorry, it will lead to a contradiction. Well, if anything leads to a contradiction, it must be false, because we can't have contradiction. A contradiction, and I'll write it up here. A contradiction is a statement that is simultaneously true and false. So contradiction is a statement simultaneously true and false, which cannot happen. Why can't it happen? Because I say so. And by that I mean, this is like basically the most fundamental assumption we make in all of math. All of math is kind of built on this idea that contradictions cannot happen. Something can't be both true and false at the same time. If you don't want to live in that world, you're free to. But then none of math is going to make sense. So the point is, if we assume that something can't be true and false at the same time, that means that if anything leads to a contradiction, it must not be true. So the point is, if this guy, if they're existing an x and d, if the opposite leads to a contradiction, the opposite can't be true. And so if the opposite can't be true, then the original statement must be true. So basically what we're saying is, if the opposite can't be true, then the original claim must be true. That's all we're doing here. This is a weird, like, awesome lawyer trick we were talking about last time. Where you go along with it, you assume it's true, but then you show that that'll lead to something ridiculous, a contradiction. So then that assumption had to be false. That's kind of clever, right? This is some brilliant stuff right here. Any questions on the idea, like our goal? Good. So that is the idea behind a contradiction proof. All right. So let's just resume what we were trying to prove last time. And so last time we were trying to prove the claim that for all, I was going to write the formal one. For all integers, right? So for all n and z, we can't have that n is both even and odd, right? And that clearly makes sense, right? I mean, based on the even and odd, based on the idea of even and odd has been burned in our brains since kindergarten, this is obviously true. But but why is it true? I bet you that's something they didn't tell you in kindergarten, right? Let's pull the curtain back on kindergarten, right, and show you what's really going on here, okay? Your kindergarten teachers, they didn't lie to you, right? but they did you no favors, right? Why is that? Why is this true? And notice, this would be very, very hard to prove directly. Because a direct proof, right, what you do is you start, a direct proof would be would say, let n be an arbitrary / particular element in Z, and that's it. That's like the only thing you're allowed to assume. In direct proof, you start with just n's in the domain, and then you try to make it work, right? You try to prove that from being in the domain, this can't be true. But we have very little to work with here. Right? Like we don't know anything about n. We don't know if it's even or it's odd. We don't know if it's divisible by 3. We have no way to rewrite it, really. It's very hard to work from here. So here's where the contradiction idea comes in. What if, instead of proving that this is true, we instead prove that it can't not be true? It's subtle, but it helps. I'll write it a different way. I'm just going to write down 1,000 different ways to think about contradiction. Contradiction proof. Prove a statement can't not be true. And how we do that? Assume it's not true, right? So assume this statement is false. And so here's the aside that we did last time. I was going to write it real quick again. So the aside we did last time, so for contradiction proof, you assume it's false. So assume there exists an n and z such that the opposite of this. So that means n is even and n is odd, right? What happened then? Well, now, because we made this assumption, we actually have something to work with, right? Knowing n is even, that gives us a foothold. We have information about n. Knowing n is odd, that gives us a foothold, right? Knowing this, that means that n equals 2k plus 1 for some k and z. Knowing this means that n equals, I'm sorry, just 2k, right? Even is 2 times something, odd is 2 times something plus 1. Knowing n is odd means n equals 2 times t plus 1 for some t. Well, then if we know these two things, we can put them back together. Okay, well, 2k must equal n, which equals 2t plus 1. So they got to equal each other, right? And then here was the key. Here's what we did last time. We said, okay, remember the whole point of contradiction is to assume the opposite of what you're trying to prove. So assume what you're trying to prove is false, meaning there exists an n, the n's even, and is odd, and then show that this assumption logically leads to a contradiction. And since contradictions can't be true, this assumption must not be true. So what this means, so we can do from here to try to find a contradiction, is let's subtract 2t from both sides. And then we factor a 2 here. We get 2 times k minus t equals 1. And if we divide by 2, we get k minus t equals 1/2. Here's the problem. K minus t is an integer. Because k is an integer and t is an integer, and as we've said a million times, the integers are closed under addition, subtraction, multiplication, not division, but they're all closed under subtraction. So what that means is k minus t is an integer. But k minus t equals 1/2. So what we're saying is, thus, 1/2 is an integer. But this is a contradiction. One half is not in Z. So the contradiction we got is to show that 1/2 is an integer, even though we know 1/2 is not an integer, right? So we just proved something ridiculous. If you start with the assumption that there actually exists an n that's even and odd, then you can prove 1/2 is an integer. But because 1/2 is not an integer, that assumption must be wrong. Otherwise, math would break. And we're going to assume math does not break. So, yeah. And so, since this is a contradiction, this assumption must be wrong. So the opposite of it must be true. Meaning for all in's not both even and odd. How's that? This is maybe the hardest thing we'll do all year, but I also think it's the most fun. I think that this is absolutely brilliant, right? The idea that we can prove that not every that every integer can't both be even and odd by showing that 1/2 is not an integer. How do we even get to that? I mean, this is brilliant stuff, right? This is really subtle things. This feels like you're tricking math. That's awesome. Any questions?
Yeah, I got a question. So when it's 2 times k minus t equals 1, could you say that since 2k minus t has to be even, and that's equal to an odd number, that itself is a contradiction, or is that not enough?
Well, excellent question. Really good question. The problem is, if you start here, you go, okay. So Herman's saying, if you look at this statement right here, that 2 times k minus, that you have this. Though this is an even number because it's divisible by 2. So that would be saying, therefore, 1 is even. But we know 1 is odd, right? Isn't that a contradiction? Well, how do we know that a number can't both be even and odd? That's exactly what we're trying to prove, right? Yeah, we're even lower level than that. That's rat right now. We're trying to prove that's true. Now, something you could do here, though, what you could do here is you could say, oh, okay, well, this right here implies that 2 divides 1, which isn't true. But why is that not true? Well, it's not true because we can prove it by contradiction. Assume it were true. If it were true, 1 would equal 2 times c for some c. And then 1/2 would equal c, where c is an integer. And then 1/2 would equal c, but 1/2 is not an integer, so you get to this point anyway. It's the same thing. And so this is a mini little contradiction proof. This is a contradiction for the exact same reason. 1/2 can't be an integer and not an integer at the same time. Anything else? Good question. Oh, Christmas colors. That's nice. Cool. So let's actually prove it. Our first contradiction proof. I'm so proud of you guys. So proof. And I'm not going to write the formal statement because this is the formal statement. I just kind of combined them. Proof. So first of all, you always tell your reader, if you're doing an indirect proof, tell your reader what you're doing. So proof by contradiction. If you're doing a direct proof, you don't have to say that. You can just get started. But for indirect proofs, always good to say this. So now, assume for contradiction that there exists an n and z, or actually, I'll do even better, that the claim is false. Now we say assume for, actually, you could also say the sake of contradiction if you want. Assume for the sake of contradiction. All it's saying is that if someone looks like, why would you assume this? Or assuming it to try to get to contradiction. We already said proof by contradiction. We're just being redundant here. Just let everyone know we're not saying this is true. We're actually saying the opposite. But anyway, yeah. So assume for the sake of contradiction, the claim is false. Thus, there exists an n and z such that n is even and n is odd. Then, now this is great, but making this assumption, we now have a foothold. Then, by definition of even, n equals 2k for some k in z. Also, similarly, I've gotten so used to saying similarly the way it's spelled, like similarly, that I don't like that now I can't say it right. It's like the people that say Wednesday instead of Wednesday. The point is I'm trying to break the habit. So I'm gonna use a lot of similes this time. But anyway, similarly, by the definition of odd, n is going to equal to t plus 1 for some t in z. Now, again, we said it before. Let's say it again. I'm actually really proud of you guys in your homework 6 because no one fell for this trap so far. But it's important that k and t are different here, right? Because we just know it's even and odd. We don't know that the k is going to be the same, right? So if you're talking about two different things, use two different variables. Yeah. Thus, n, or I'll say 2k equals n, which equals 2t plus 1. Hence, 2k equals 2t plus 1 by the transitive property. Transitive because of 2k equals n and n equals 2t plus 1. The transitive property tells us 2k equals 2t plus 1. And then next from that, we can get that 2k minus 2t equals 1 by subtracting 2t from both sides. From algebra, we know that we can always subtract the same thing from both sides and the equation's still true. Now here, this is going to be, we can factor this. So this is true by factoring. And then this only happens if k minus t equals 1/2. This implies k minus t equals 1/2. We can get that by dividing 2 from both sides. And I'll say here, note 2 does not equal 0. The only reason you're noting that is because you can't divide by 0. And so whenever you're dividing, you have to make sure you're dividing by isn't 0. It's really obvious here. Sometimes not so obvious. Yeah. So we just proved k minus t equals 1/2. And this should be a problem, as we already talked about, because k and t are integers, so k minus t should be an integer. Note, since k and t are in z, and z is closed under subtraction, k minus t is n z. Thus, 1/2, which equals k minus t, is n z. And this is the beautiful part. We have just proven something ridiculous that we know is wrong. We started with an assumption and logically show from that assumption that something incorrect is true. Therefore, that assumption must not be the case, right? So this cannot be true, right? And we put a little arrow here. We put two arrows going against each other because that's kind of like symbolizes contradiction, like two things going against each other. And so we say contradiction. I like to put exclamation points. Technically, everyone I talk to tells me not to, but I don't care. Okay, I like it. I will put it on a mathematical proof. If you're good enough, we'll let you do it. Contradiction. 1/2 is not in Z. Therefore, our assumption is incorrect. Thus, for all n and z, n can't both be even and odd. Square. Done. You guys can't see that. No, you can. How is that? Come on. That's pretty good, right? This is a absolutely, totally formal, rigorous proof that numbers can't both be even and odd. Something that's so obvious, but so hard to prove. But we just did it. And the way we did it is brilliant. It's not by going at it directly, right? It's by kind of being a little coy with it, right? Going like, okay, assume it did happen. And then show that leads to ridiculousness. It leads to 1/2 being an integer, which it's not. I mean, this is like, I mean, you can use it for anything. It's not even a math thing. It's a lawyer thing. It's a philosophy thing. Like imagine, I went over to my friend's house and the grandma made some like disgusting peanut butter salad, right? And I was like, oh no, I'm sorry, I can't eat that. I have a peanut allergy, right? And then like 2 days later, you see me gobbling down a PB&J. Right. The point is, if they were like, if the grandma was like, oh, you know, he's a peanut allergy, but actually, wait a minute, I saw him eating a peanut butter and jelly, that contradicts the peanut allergy. That's not a good example. The point is though, if you assume an incorrect thing and then prove it leads to ridiculousness, that proves it's incorrect. Any questions? Is this making sense? Good. Good. Come on, this is kind of cool, right? Oh, you wait. You don't think it's cool now, you just wait. All right. So that is a contradiction proof. So now we've done one contrapositive proof and one contradiction proof. Let's go back to contrapositive. Just to shake things up, we're just going to do some examples. Get some muscle memory here. So let's try to prove the claim. And this is the one I attempted last time, but I had it all complicated, more complicated than it needed to be. Here's the claim. I'm just going to write it in the math formal way. For all P in our set of primes, and for all A and Z, and for all B and Z, P not dividing A and P not dividing B implies P does not divide AB. Now, this is kind of a mouthful, right? What this is saying is that if you have two numbers, A and B, and P is a prime, if P doesn't divide A and it doesn't divide B, it can't divide their multiple, their product, which is kind of weird, by the way. Because I mean, let's think about it. For example, 10 does not divide 6, and 10 does not divide, let's say 5, right? But 10 does divide 30, which equals 5 times 6, right? So just because 10 didn't divide both of those doesn't mean it doesn't divide the product. But 10's not prime. What I'm saying is that for any prime number, if P doesn't divide the first one, or P doesn't divide the second one, it won't divide the product. That's interesting. And this sounds benign, but it's actually one of the fundamental parts of primes and is used in a bunch of high-level math, abstract algebra. It's pretty crazy. Anyway, let's do a side. First of all, do we think it's true or false? Let's kind of, like, one way to go about it is let's kind of try on our own to kind of prove it false. Like, what do you guys want to try? And actually, while you're thinking about that, here's a time where I will mention an important fact that we need for this problem, and that is the fundamental theorem of arithmetic. What that says is that every natural number, actually, so we could, it's the same principle, but it's a little more complicated with negative numbers. Let's just say this. For every natural number, can be written uniquely as the product of primes. In this unique business, it's uniquely up to order. So what that's saying is that 24, for example, equals 2 cubed times 3. Or you can write 2 times 2 times 2 times 3. Right? So it's the product of primes. It also equals, and this is unique, it also equals 2 times 3 times 2 times 2. So you can switch around the order of the primes, but the point is they're all going to be there in the same numbers. We went over that before. So, how do we prove this? Well, if we try to go directly, we're going to have a hard time. Because P not dividing A, what that means is that there doesn't exist an integer. This means there does not exist an integer such that A equals PK. But this is like a negative. We're not saying A equals PK. Like, it's really nice. Like, this is like the foothold thing I'm talking about, right? It'd be really nice if we had this, but we're actually saying there doesn't exist an integer for this to happen. So we don't really know anything. We know this can't happen, but that's kind of, we're not saying much. Like, anything else could happen but this. That's like how do you work with that? So here was a bright idea.
I mean, I think we should use the contrapositive. I don't know why, but
I think that's a fantastic idea. Well, Benet, you remind me of me. Good job. Good job. Yes, Benet is very clever. And also maybe the only one willing to talk. And that is, we should use the contrapositive. Because if we look at the contrapositive of this, which remember is equivalent to the original statement, the contrapositive is, says, for all P, I'm going to go over this part, blah, blah, that the contrapositive of this conditional is that P divides AB implies that we don't have this. So the contrapositive, right, you take the negation of this, implies the negation of this. So the negation of P doesn't imply AB is that, well, P does imply AB, or divides, P does divide AB. And then this will imply the negation of P doesn't divide A and P doesn't divide B. But by De Morgan's law, right, this is saying that P divides AB implies that P divides A, or P divides B. Right? Just distribute that negation and flip B into an OR. This is much better. This is so much better because now we get to assume, now we should have proved this. We can assume the hypothesis. So we get to assume that P divides AB. And since P divides AB, we know there exists a K such that PK equals AB. And that's huge, right? Now we actually have an equality we can play with. If we have an inequality, you know, you can't really do anything with that. Does that make sense? Why the contradiction is the same as this and why that might help? Okay, then. So let's work on this, right? First of all, notice that by the fundamental theorem of arithmetic, each of these guys has a unique prime decomposition, meaning a unique way to write them as a product of primes. So I'm going to say, let's go ahead and let K equal, let's just call it P1 all the way out to PT. That'll be K. And this is K's prime decomposition. And then A, that's going to equal Q1 out to QS, where all the Q's here are primes. Like, we just know that this does happen. Since A and K are natural numbers, right? Like, we can write them as a product of primes. And then same thing with B. Let's say R1 out to, we need some last index. Let's just say M. R1 out to Rm. This is B's prime decomposition. We know these have to exist. But then, if we substitute them into this formula here, we get P times P1 out to PT equals R1 out to Rm times, oh no, equals Q1 times Qn times R1 times Rm. This is the prime decomposition of the left side. This is the prime decomposition of the right side. Now, what does the fundamental theorem of arithmetic tell us about these two prime decompositions? Oh. Oh, wait, we just say Prime Day? Is that like Amazon Prime Day? That would have been good. Would have been good. Where do you think I got all my knickknacks from? Those grow on trees. Yeah, actually, nothing more knickknacks is wood, so yeah, they don't grow on trees. Yeah. The fundamental theorem of arithmetic says that every natural number can be written uniquely as a product of primes. And since PK and AB equal each other, PK and AB are the same number. Are the same number. And since PK and AB are the same number, they have the same prime decomposition. Up to ordering, right? It's unique. So that means this prime decomposition is the same as this prime decomposition. Let me give you an example, right? For example, 3 divides, let's say 45. Or 3 divides 10 times, 10 times 9, let's say. Right? So that means that there's some k such that 3k equals 10 times 9. And that k, we just know 10 times 9 is 90, so that k is 30. And now let's break down these prime decompositions here. So 3 is already prime, so its prime decomposition is itself. But 30, that breaks down into what? 2 times 15? But 2 times 15 is 3 times 5? And this breaks into 2 times 5 for 10, and 3 times 3 for 9. Notice, these are the exact same prime decompositions, just in a different order, but they're the same, right? Like the same numbers are there. And that's not a coincidence. That always happens for any of this stuff because of what we just talked about. Now, here's the big thing to notice, right? If the prime decompositions are the same, that means that P that's in the prime decomposition on the left side must be in the prime decomposition on the right side. It's got to be over here. In our case, in this example, 3 is over here. It's got to be. If it's not, if P doesn't show up over here, well, that means that this prime decomposition is different from this prime decomposition. We know that can't be true because prime decompositions are unique. Is this making sense? So that means that P has got to equal Qi for one of these i's, or it's got to equal Rj for one of these j's, or for one of these guys. It's got to be one of these. It's got to be in here or here. But if it's one of the Qi's, well, remember, A equals that, so that means P divides A. Or if it's one of the R's, well, B equals the multiplication of the R's, so that means P's in here somewhere, so P would divide B. So P's got to divide A or B. Hit me with questions. I felt really soulful the way I asked that. That was very nice, very peaceful. No questions? Are you sure? Does that make this make sense, or does that mean you don't even know where to start? I hope it's the first one. Okay, so let's think positive thoughts and get to the formal proof. So there's kind of two things going on here. I kind of combined two lessons in one. Number one, contradiction made things easier. Why did contradiction make things easier? It gave us this foothold. Rather than assuming that P does not divide A and P does not divide B, something that it's just hard to get your hands on. It tells us we can flip it and we can do the contrapositive part of it, which gives P divides A, B implies this. That's much better. That gives us something that we can actually work with down here. That's the contradiction part. If you get that, you understand contradiction. It's good. The rest of this was some practice with our fundamental theorem of arithmetic. And it all comes down to the fact that that every number can be broken down to primes uniquely. Hot damn. Okay, let's go on. And actually prove this. And I'm going to erase this just in case we need the room. But I hope we know what that means. I can write down again if I want. Proof. And I'll say, start off, since we're not doing a direct proof, you always tell your reader what you're doing. What we're doing here is proof by contrapositive. Proof by contrapositive. And so you can even note, if you want, you don't have to say this, but you can. So we're trying to show that for all P and primes and for all A the natural numbers, for all b the natural numbers, p divides ab implies p divides a, or p divides b. That's more for you guys. Just let us know what we're doing. Because this does in fact equal, this predicate right here is equivalent to p divides ab implies p divides a, p divides b. We talked about that already? Cool. So now we can just do a normal direct proof. We do a direct proof trying to prove the contrapositive instead of the original statement. So now it's kind of like we know. Let's go ahead and let P be an arbitrary but particular prime number, and A and B be arbitrary but particular in natural numbers. So that's the domain. We're saying these things are in the domain. Now assume, we're going to assume the hypothesis. Since we're no proof by contradiction, assume the hypothesis of the contradiction. So assume P divides AB. This is the whole reason why contradiction is beautiful, because this is our foothold. This is exactly what we want. I hope you guys understand what footholds mean. If not, start climbing. It's fun. So assume P divides AB. Then by definition, there exists a K in Z such that PK equals AB. Now here's the part in the aside where we broke everything down as prime decomposition. So we know A is a prime decomposition because it's a natural number. And we know B is a prime decomposition because it's a natural number. And we know P is prime, so it's its own prime decomposition. K, we know it's an integer, but by the definition it divides. We don't know yet it's a natural number. We haven't proven it's positive. It's going to turn out to be positive because, and we're going to prove it right now. So I'll say note K equals AB over P. So since A, B, and P are positive, K, which equals AB over P, is positive. Thus, K is a positive integer. The same thing as being natural numbers. Little technical detail there. I almost left it out, but I thought, no, I'll get a good example and show all the details. So now we get to the fun part. Thus, since K is in N, by fundamental theorem of arithmetic, FTOA, I'm going to abbreviate it. Do you know why I abbreviate it that way? Because the first letter of F, fundamental theorem of you guys get it. I once said somebody, I hope we all get this, but there exists the backward Z because it's E, like exists, all right? And for all is an upside down A because it's A, like for all. That's a really easy way to remember it. Like I wanted a person, like when I was taking this class back in the day, like whisper like, hey, I found out a way to memorize there exists in the for all. Like the backwards E is E, like there exists. And so down A is A, like for all. And I was like, yeah, that's why it's like that. Anyway, the point is, if you didn't know, now you know. So this is fundamental theorem of arithmetic. So since k is a natural number by the fundamental theorem of arithmetic, there exists, what do I call it? R1 through RT primes such that k equals R1 times R2 all the way out to times RT. It also says that it's going to be unique. So maybe you could even say there exist unique primes. Right now we just care that there exist primes. Further, since A and B are in N by the fundamental theorem of arithmetic, there exists, there exists, oh, I got this backwards. It'll all be fine. Q1 through QS primes, and there exists, what's a good letter? I don't want to use P again. Or A or B. C doesn't feel very prime. U, we'll use U. There exists U1 through UM primes such that A equals Q1 out to QS and B equals U1 multiplied by U2 multiplied by UN. So this is just A written as a product of primes, this is B written as a product of primes, this is K written as a product of primes. You have the letters different than the SI, but it's the same idea. Now here's where the brilliant part comes in. Thus, PK equals AB if and only if P times K is going to be R1 times R2 out to RT equals A, which is Q1 times Q2 out to QS times B, which is U1 times U2 out to UM by substitution. Now, note the left and right sides are both prime, or I'll say products of primes, i.e. Prime decompositions for PK which equals AB. They're the same number. So these are both prime decompositions for the same number. Like we were saying before, by the fundamental theorem of arithmetic, prime decompositions are unique. Then, since prime decompositions are unique up to ordering by the fundamental theorem of arithmetic, since we know that, the left side, P times R1 has R2 all the way to RT. And the right side, Q1 out to QS times U1 out to UM must just be reorderings of each other. Oops. Does that make sense? That's the whole idea, right? We wrote the left side and the right side in two different ways, right? Because they're equal to each other, and because prime decompositions must be unique up to ordering, that means these guys must be reorderings of each other. Okay. I'm gonna erase the top part of this proof. Continued. No, this is not standard erasing proof. I'm going back to the beginning. You should probably just write all your proofs on paper because I won't know what you erased. But other than that, copy me exactly. Yeah. So this proof, we know that these two are reorderings of each other. Thus, the prime P on the left side must be in R1 out to RS. No, sorry, Q1 out to QS or U1 out to UM. Right? It's gotta be one of these. Thus, P either equals, so thus P is either in or P is in U1 and UM, right? We know one of those is true, maybe both. Because nothing saying that both A and B can't be divisible by P. Let's do case one. P is in Q1 out to QM. Thus, P equals to QI for some I in the index. Wait, this should be S here, I'm sorry. Some I in the index. Then, can someone remind me where these cubes come from? Like where were they originally defined? What does Q1 does 2Q all the way up to QS equal?
Is that not the FTOA?
Oh, we have to use the fundamental arithmetic, but I'm saying, I legitimately forget. Is this B or A?
Oh.
It's A?
Yeah, I think so.
A equals Q1 out to QS or I'll say there's going to be some I minus 1 times qi times 2i plus 1 out to q. Actually, I should write it like this. Qi's in there somewhere out to qs, which equals q1 times p all the way out to qs. I'm just saying p is a factor in there somewhere. Thus, since q1 thus since all the q's are primes, they are integers. So A is an integer multiple of P. It's going to be P times a bunch of integers. Thus P divides A. The technicalities here are a little complicated, but the point is, yeah, the point is, if P is in one of these, if P is one of the Q's, well, A is just the product of all the Q's. So that means P divides A. It's in there somewhere. P, there's, yeah. I hope that makes sense. Case 2. I'll erase this now. Oh, over time, but it's the exact same thing. If P is in U1 out to UM, thus P equals UJ for some J in the index from 1 to M, then since B equals U1 times U2 out to UM, which equals U1, there's going to be a UJ in there somewhere, times UN, which equals U1 times P out to UM. B is an integer multiple of P. Thus, P divides B. Therefore, in either case, P divides A or P divides B as desired. Woo! That was long. That's way longer than any proof I'll ever ask you to do, and probably a little more complicated than any proof. Yeah, definitely more complicated than proof I'll tell you to do. But if you can understand that, you get it. You really get it. This is contradiction mixed with fundamental arithmetic, all combined. So, yeah, so the contradiction takeaway is that instead of proving P doesn't divide A, P doesn't divide B implies P does not divide AB, you prove the contradiction. P divides AB, then P divides A, or P divides B. This gave us the foothold we needed to get our hands on the math, start using our definitions and things to actually prove something. The rest of it is just playing around with the fundamental theorem of arithmetic, which I think is kind of obvious, but also kind of not. The whole thing to get around is that primes are the atoms of integers, and they can only be broken down into those atoms in a unique way. So you start to see things like this. Any questions? Well, we didn't get to the most beautiful theorem at all, math. That will have to wait till next time. But until then, it's Thursday, basically Friday. It's people's favorite day. Have a good weekend, everybody. Friday's basically a weekend. Have a great weekend. Yeah, that's all I'm going to say. Have a great Thursday night. Have fun on Red Assignment 7 if you haven't already done it already. I know you people don't procrastinate. Look at you. The cream of the crop here? No way. Okay, well, I'm going to stop sharing, stop recording, people. Thanks for the good class.
Thank you.
Thank
Welcome,
you.